circular motion and gravitation. So, objects moving in a circle, I think we've kind of, made sense of this, but objects moving in a circle, they have a net force on them, even if they're not changing speed. So, on Newton's first law, an object in motion will stay in motion. If this has a velocity this way, right, without any force, it'll just move down that path, but it needs a force to really move in a circle, and that force happens to be pointing to the center of this circle. So if we draw sort of that FBD, and this is like a top view, you could see that that force is going to be pointing towards the actual center. So what's going to happen is as this force points towards the center, it's going to continuously be changing its sort of direction, and it's going to be moving in a circle. And so, and this point, it's the same distance away, but this time its velocity is still, the speed is still the same, but it's just moving straight down. If I were to, if I were to let go and stop producing or stop applying any force, it would just follow that straight path. This velocity is always tangent to the circle, right? No matter where on the circle you are, it'll always be a tangent. The force is just now going to point inwards. And I'll call this like F and F, right? So even though the force is pointing inwards, because it already has velocity that way, it's not just going to fall towards the it's not going to fall towards the middle. That velocity is going to change directions throughout the circle, and it's going to go to constant speed. It's going to go to constant speed because during the entire time, the force is like perpendicular with the velocity. If the force points in the same direction as velocity, then it'll speed up. If it's pointing in the opposite direction, it's going to slow down, and if it's perpendicular, it's just going to change direction. So I hope that kind of made sense in terms of the conceptual part of circular motion. Just the idea of a centripetal, which means center-seeking force. Like at this entire time, that force is always going to point inwards to the center for circular motion. So this is a horizontal circle, so we don't really have to worry about gravity. This is just a top view. Let's try to mathematically model circular motion. And you can do the lab and kind of figure out this on your own. But really, what it comes down to is that an object is going to have a certain mass m, moving at a certain speed v, and it's going to be a distance from the center, and we'll call that distance r. It's just going to be the radius of the circle. It's really just the distance from the middle radius of the circle. Okay, I'm repeating myself. The whole point is if an object with a mass m wants to move with a velocity v, and I'll kind of make these like variables. It wants to a mass m, velocity v, and a radius r. These numbers could be anything. It could be 10 kilograms, 20 meters per second, 30 meters. In order to move with this, in order to move a mass in a circle with this m, this v, and this r, you're going to need a certain F net. And that F net is going to be equal to m v squared over r. Okay, so what this is saying is that if you have a mass with velocity v and radius r, you need this much F net to move in this kind of a circle, right? If that mass increases, you're going to need more F net. If the speed increases, you're going to need more F net to stay in that circle with the same like m and r. And then if your radius increases, to go in a circle with the same m and v, you're going to need more r if you want less radius, right? So, right, we're just assuming that two of these are constant. If we change one of them, we can see how the F net needed is going to change, right? So, this equation, this is our centripetal force equation. Now, really, what this equation really is let me kind of do it here. If we have F net, Newton's second law equals ma, really, on your equation sheet, you'll see this. The F net is just m times the centripetal acceleration, which is v squared over r. So if we say AC is equal to v squared over r, we can see how we just substitute acceleration in, and that's the equation. And you can search up all sorts of proofs or derivations for where this equation comes from. It's pretty cool, but yeah, that is really what the equation is. So for horizontal circles, it's pretty simple. This is F net C just equal to mv squared over r. So if you have something like a ball, and I'm like tethering it around in this circle with a rope, we can imagine that force is going to be force tension. If we think about something like the moon, and we'll talk about gravity too, but if we think about the moon, that force that is pointing inward for this entire circular motion, which isn't exactly circular, but it's close enough, it's going to be force gravity, right, Fg. Now, what's really interesting is if you have something like on a disk, so let me draw I'm going to kind of erase this model. If we have something like on a disk, so if it's like a record player or something, you will actually see that if you place like a little mass on here, I'm not going to make it 3D, if you just place like a little mass here, it's going to move in a circle, and then that force that is pointing to the center of that disk as it rotates around is going to be friction, right? Because friction is stopping it from just sliding off completely. Friction is the thing that's sort of keeping it tethered and moving in a circle. And the same thing goes for cars. So if you imagine, this is like a street, if we have a car, that force, let's do it like here, that force is going to point inwards to sort of that radius of the turn. Like if you imagine the turn being like a little section of the circle, it's going to point towards the center, right, as it's turning at all times. So force friction, I guess I'll write this, like horizontal, for horizontal F net, I don't know how to say it, horizontal circles, I'll just say that. For horizontal circles, the forces that can cause circular motion are like force tension, force friction, and then force gravity. So what's really interesting is that for force friction, it's static friction, right? And you can kind of think about why it's static friction, because that's actually a question I asked my physics teacher. I'm not 100% sure why it's static friction. But with that said, static friction has a maximum. So for that so if we think about F net C, and I'm going to kind of go over this because I know it's kind of a big thing. If we have F net is equal to force friction, so that is the F net. This is just what this equation is saying, and then we can substitute F net for mv squared over r equals force friction. Because of static friction, we always know that force friction is going to be less than or greater than Fn times mu. Let's say we want to figure out like how fast can I make this turn? Well, figure out how fast you can make that turn. If you go too fast, you know what's going to happen. You're going to crash and not make the complete turn. The maximum speed is when there is enough friction to kind of make the turn, and that's going to act at a maximum. So if we take the force friction equation, this is the maximum value, right? It's always less than or equal to. Just substitute that in, mv squared over r is going to equal Fn times mu, and then Fn is just Fg, so we can just kind of put mg mu. The mass cancels out. And then you can figure out that v squared over r is going to equal g times mu. So then v is just square root g times r times mu. What's kind of interesting is, mass cancels out. And mathematically, we can see that. Conceptually, just thinking about it, go back to this idea of like the amount of net force you need. If you increase your mass, right, for the same speed and the same radius, and the same speed is like the max speed, right? So if you increase your mass, you need more F net in order to move in a circle. But because force friction, right, is equal to Fn times mu, that looks like an n, it should be a mu, which is equal to mg times mu, when you have more mass, you're going to get more force friction. So even though you need more F net in order to move in this circle, you get more F net, right? It's kind of this reoccurring idea that, if you have more mass, you have more inertia, but then you also get more force when you're dealing with gravity. So Just kind of trying to conceptualize that. Okay, and obviously this only works for like friction, right? If the mass increases for like tension, yeah, you're gonna need more tension. So for like a rope. So yeah, that's horizontal circles for you. Let's go on to vertical circles, and then we'll talk about gravity as well. I'll kind of touch on that. So for vertical circles, it's very interesting. I always like, let's do a couple examples. So if we're going up a circular sort of ramp here, and we're like a little car, what you're going to notice is that, let's think about the forces on you, the entire, so let's say you're moving this way. So for the forces on you, we have, we're always going to have that Fg pointing down. That's kind of a rule. Fg always points down on Earth. Okay? And then there's always going to be that normal force. And it's going to act perpendicular to the surface. So a common thing that we're kind of used to is saying that, hey, the force normal is equal to Fg, right? Because when you're not accelerating and you're at rest or whatever, there's no vertical acceleration, so your forces must balance out. But there is a centripetal acceleration this entire time around. So the Fn needs to be less than Fg. It has to be. If these forces are equal, it's not going to move in a circle. It's not going to have that centripetal acceleration. A very common thing they'll ask is, okay, you're given, let's just say we're given the mass, we're given the radius of this circle. You're given the radius, you're given the speed, actually no, not speed. We want to figure out what's the fastest it can go. So what I want you to try, like if you're in the middle of an AP test and you're like, oh, I don't know, what you can try is take something like AirPods, or, well, you can't have AirPods, just take something. This probably won't work in the AP test. But what you can do is you can actually sort of model that, motion, right? And then you can see that it feels kind of light. Like as at the top, it feels a little bit lighter. Like there's not as much force being exerted. And then you could try going really fast, and you can see, like if you do it really, no shit. If you do it really fast, it's gonna go falling. So just to kind of conceptualize that, right? Just kind of getting a feel for what that means. What's going on is that as you go faster and faster, let's think about this equation. So Fnet, the amount of Fnet you need is going to be equal to mv squared over r. Well, what is the Fnet? Well, the centripetal net force is going to be all the inward pointing forces minus the outward pointing forces. So we think about Fg minus Fn, right, is going to equal mv squared over r. Now, m is going to stay constant. Let's think about what happens if the speed gets faster. Now, in order to keep moving in a circle with the speed of v, you're going to need more Fnet. Now, how is this whole number, how could it get bigger? Well, it's going to get bigger by Fn. The only thing that can change, I should say, is Fn. Fn has to decrease, right, in order to subtract less and have more of a number. My dad is doing some, I don't know, he's being goofy. But you could see that Fg you can't change because it's equal to mg. It's impossible to change your weight on Earth. But your force normal can for sure decrease. If you keep increasing it more and more, your Fn has to decrease more and more. But there's a magical sort of point, and I'll try to find a video, I don't know, I'll link it, where your Fn is 0. Think about it. If your Fn 0, you're just left with mg, which is equal to mv squared over r. If your speed gets any bigger now, we're to the point where Fn is so small that it's just 0. If your speed gets any bigger, you're cooked, right? Like you're not going to be able to move in a circle because you can't get more Fnet. That is kind of the main idea, to find the centripetal, or the speed at the maximum speed of any sort of hill or turn. And then obviously your m's cancel out, and you can figure out that if v squared over r, that is our centripetal acceleration. In other words, g is equal to ac. at the maximum speed, your car is actually in free fall. Like it's not touching any, like Fn is 0. It's not like, for that instant, the acceleration is g, therefore it is in free fall. The only force is Fg, so that's pretty cool. Okay, I'm not going to go through all of these steps for each sort of scenario I'm about to cover for vertical circles, but I'm going to go over sort of some things to kind of keep in mind. So some scenarios would include like this. We have the scenario of, and I'll switch back to blue here. We have the scenario of an upside down vertical loop. And right? And then another scenario would be, what's the other scenario where like there's a third, but this might just be maybe. So let's kind of go through each of these. We talked about this one, and then we talked about, let's talk about this one. So I'm going to go over this very quickly, but using the same idea that, let's think about the forces. We have Fg, and then we could have some Fn. We don't know how much, but there could just be some Fn. Fn could be bigger than Fg, and we'll talk about that. If we think about the net force, it's going to be all inward, right? It's all inward, so we could say Fg plus Fn equals mv squared over r. In fact, and then we can do it the same thing for this, but instead of Fg minus Fn, now Fg is pointing outwards, and Fn is pointing inwards. So Fn is going to be bigger than Fg. We can say Fn minus Fg equals mv squared over r. So what you can see is that when you increase when you increase v, you're going to need more centripetal force, but that's not an issue, because Fn can just get bigger forever. That's not an issue. Fn can get as big as you need it to be. And now, obviously, in the real world, I think engineering-wise, like that's not actually true. But with like Fn, it'll just get bigger and bigger. There's not an issue. You can go as fast as you want, right? Fn will just get bigger and bigger and bigger. So there you go. Now, for the same thing though, if you go slower and slower and slower, Fn has to decrease. It has to. Because Fg, we've established, cannot change. Fn has to decrease so that there's less net force. Not so much as an issue for, not so much as an issue here, right? Because when v is equal to 0, Fn is just going to be equal to Fg. So Fn minus Fg is 0. Like that's, it's not going to be accelerating. This is not an issue. What we have an issue with slowing down is that when you go slower and slower and slower, your Fn is going to get smaller and smaller and smaller. It's going to get to a point where if you go too low, if you go too low, then this is going to be 0. You're going to have Fg is equal to mv squared over r. And what's really interesting is if you get any smaller, you have too much net force. Like Fg is going to be bigger. You're not going to be able to go in a circle with this m and with this mass and this radius, right? You're actually going to go, if this stays the same, your radius. Oh wait, no. Your radius would also decrease in order to make everything the same. So like what you would see is if you have like a water bucket and you go too slow, the water, like it's gonna spill sort of at a smaller sort of radius. Not really a circle now, but hopefully you can see that it's a smaller radius-ish than the loop. You don't really have to worry about explaining that necessarily, but just getting the idea of that if you go too slow, there's a minimum speed, right? Like if you cancel out the m's, because this is just mg, we have g is equal to v squared over r. Now there's a minimum speed, because if you get any smaller, we're gonna have issues. So that's how you figure out minimum speed, maximum speed, and then there is not really a minimum or max. The minimum would be 0, I guess, right? Because if you're not moving, then you're just not moving in a circle. So cool stuff. I think, let's see how much time we're at. That's kind of everything, I hope. I hope that's everything for circular motion. I think that's kind of the big ideas. I think everything else you can just get your way through. And I'm going to talk about now gravity. So for gravity, so some key things to mind, or to note. If you have like the Earth and you have the Moon, they're at a certain distance, and there's obviously the force keeping them together. Yes, there's the force that's stopping the Moon from just going at its constant velocity. There's gravity. Now that gravity, we can't use Fg equals mg. Fg equals mg, we know we can figure out the mass of the Moon, sure, whatever, but g is not 9.8 in space, right? Like on Jupiter, g is 24, and on Mars it's 6.7. G is not always 9.8, little g at least. We need a better equation that works for things in space, and the equation we can do to do that is Fg equals g, big G, m1, big M, little m, doesn't really matter which mass, like you don't have to do this more, but g, big M, little m, m1, m2 over r squared. R being the distance. It's not always like a circle. Like the r between me and the center of the Earth, and yeah, this is on split centers. It's not, even though I'm not moving in a circle, that's just what r is. So this is pretty cool. This is a pretty cool equation. You can figure out the force, and what you can actually do is if you are moving in a circle, if you know this distance, what you can do is be like, okay, well, Fg is the centripetal net force, so this will be equal to mv squared over r. And then using some algebra, we can like sort of cancel out the little m's. We have v squared, and then we can multiply everything by r. We get gm is equal to gm over r. And then you can take the square root, and you can get an equation for the speed of the thing. What do you call it? The speed of why am I blanking? The Moon or whatever. You can figure out how fast it's moving. And then if you take v, this is the same as 2 pi r over the period. You can calculate like the period, like how long a year is on Venus or something, just based off the radius and then the mass of whatever you're orbiting, the big M. So yeah, that's really just what you need to know about gravity and how you can use that equation. And remember, the only force is gravity, so that means the Moon is technically in free fall. Like it's falling, like it's falling this way, but it also has speed this way, so it like sort of falls sideways. That's kind of how think about it. I'm really clumsy with this stuff, but yeah, that's why like astronauts on the like space station, like they're very close to the center, like to the Earth. Like, that's them, right? But they still have a lot of gravity from Earth because we, you know, g big M little m over r squared. They have a lot of gravity, but they're in free fall and they're sort of circling and everything is falling together, and it creates a sense of weightlessness. If you ever, I don't know, jump off a cliff or something, you don't do that, but you can like take off your glasses, you can take like something from your phone, it'll all float around you. Same sensation. It's the exact same sensation. So yeah, that's really a summary of hopefully every big concept in Unit 3. I'm trying to keep these videos not too overwhelming. There's a lot, I can go over like every worksheet, but it's just too much. I think if you can conceptually understand this and know how to use the equations, I think you'll be A-okay. So yeah, thank you for watching, and good luck with your studying and tests.